A number theory problem can be reconceptualized as a geometry problem. My thesis investigates a geometric reconceptualization of the Littlewood conjecture. Terms of the sequence are simultaneous rational approximations of two numbers. The rate of convergence is still an open question for some irrational cases. The notation indicates distance to the nearest integer. The set of exceptions to the conjecture must have Lebesgue measure 0 and Hansdorff dimension 0. Littlewood went into Cambridge University at age 18 in 1903 and stayed through 2 world wars. He preferred to collaborate. 2 famous collaborators had not been recognized for their abilities before working with Littlewood. Ramanujan, a young, unknown, self-taught math prodigy from India, who was recruited to Cambridge by Professors Hardy and Littlewood, and worked with them, unpacking his discoveries until his death 5 years later. They made the recent movie Man Who Saw Infinity, The Origins of String Theory. Mary Cartwright, Littlewood played a pivotal role in her early career. Wartime collaboration was on signal processing data. Contributions included origins of chaos theory and early work on the butterfly effect. Together, they significantly influenced the direction of dynamic systems theory. This is the main theorem of my thesis. For the next 20 minutes, I will explain how pivot points in dual lattices relate to the Littlewood conjecture. On a one-dimensional number line, multiples of an irrational do not strictly approach integer values. By the Littlewood notation, we are seeking a convergent subsequence. Badly approximable numbers. By the definition of badly approximable numbers, we see that no iterative term of any subsequence approaches 0 because the iterating variable n increases too rapidly and the distance to the closest integer contracts too slowly. The class of badly approximable numbers includes irrational quadratic roots. The volume of a box. When we observe the 3 dimensions of the Littlewood sequence terms, we note the similarity to the volume of a box of integer height. Can we recast the Littlewood conjecture geometrically as the changing volumes of a sequence of boxes? A vector with irrational coordinates. Passing through a 3-dimensional integer lattice. At every fixed integer height, there is a two-dimensional, horizontal integer lattice. At every integer height, there exists some square of lattice points around the irrational point of intersection by the pigeonhole principle. Looking closer at the horizontal square at some integer height n, distance in the x direction or the y direction is bounded by 1/2. At any integer height n, there will exist a rectangular box from the vertices of any square. The height of the box is n, then the volume of the box must also be n. An irrational point at height n. The box we desire to represent, the Littlewood sequence terms, will be cut from the corner of the integer square. The point of intersection of the irrational vector with the horizontal plane determines the irrational box. The opposite vertices at height 2 are the irrational point and the integer lattice point. Sequence of the volume of the box at each height n. A geometric interpretation of the Littlewood sequence. This geometric representation is isomorphic to the Littlewood sequence of terms. A transvection to shear the lattice. The transvection is a transformation that shears the lattice points horizontally. Each height in the horizontal plane is preserved and shifted. The irrational vector becomes the z-axis. One symmetric sheared pivot box. We remake our pivot boxes to be symmetric about the origin. Resolves the computation of positive and negative coordinates. 8 times the volume of the Littlewood conjecture. Distances from the nearest sheared lattice point to the z-axis is bounded by 1/2 in the x direction and by 1/2 in the y direction. The lattice point will be optimal when the symmetric convex body contains no non-zero lattice points, in the sense of the Minkowski convex body theorem. Choosing only the subsequence of pivot boxes which contain no non-zero lattice points. This is the unique crystalline-looking structure that corresponds to these particular two irrational numbers, the square root of 2 and the square root of 3. This is also, in a sense, an optimal Minkowski construction, as it contains no non-zero lattice points, and it may increase in volume indefinitely, while being bounded by 1/2 in the x direction or 1/2 in the y direction. The sequence is strictly improving, but only in one dimension at a time, either narrower in the x direction or more narrow in the y direction. But notice that in the other direction it may expand, but still must be bounded by 1/2. In her San Francisco State University thesis, Liu demonstrated that the sequence of pivot boxes and the Littlewood sequence share the same infimum. Transference theorems are important relationships between elements in a lattice and their corresponding set of dual elements. Here is the definition of the dual lattice. The vector product must be an integer value. The integer lattice is self-dual. A particular balancing transformation, A, that acts upon a pivot to uniquely convert that pivot into a balanced pivot, that is, a vector with 3 coordinates of equal magnitude. Balancing theorem by San Francisco State University students Lucy Odom and Donald Lee. For every pivot, there exists a balancing transformation that acts upon the lattice and balances the particular pivot. Balancing preserves the pivot-dual pivot relationship. The coset decomposition theorem by San Francisco State University student Donald Lee. The dual lattice of a balanced lattice will be decomposed into cosets. The equation for the cosets and the distance between cosets will be determined by r star, the common coordinate of the balanced pivot. Decomposing a 3-dimensional lattice. An infinite sequence of 2-dimensional cosets. A 3-dimensional lattice is generated by 3 linearly independent basis vectors. Each coset has the same 2 generating basis vectors. Each coset is separated by the 3rd generating basis vector, u tilde. The first coset plane intersects the corners of the pivot boxes for generating basis vectors v and w, severing triangle regions. The triangle regions lie upon the first coset plane. We have 2 basis vectors for directed line segments emanating from a point of origin in 3-dimensional space. So each basis vector has a direction and a length. And from each basis vector, we are able to create a symmetric box where the basis vector begins at the center of the box at the point of origin, 3-dimensional space, and travels to the corner of the box. Therefore, the coordinates of the basis vector become positive and negative coordinates of the vertices of the box. Our second basis vector allows us to create a second concentric box. So the 2 boxes have the same center because the 2 basis vectors were also concentric.
starting at the origin to the center of the box, we're able to create a symmetric box and a second symmetric box, both concentric, each created by a basis vector. If we then pass a plane through three-dimensional space, it cuts through the corner of each box, the same plane cutting through both corners. In each corner, the box created by the yellow basis vector will cut off a triangle region associated with the plane as it cuts through the corner of the box. And the box determined by the red basis vector, as the plane cuts the corner of the box, will cut loose a red triangle region on the corner of this box. Therefore, from the two basis vectors, we were able to determine two concentric boxes that are symmetric about the origin, both above the z equals 0 plane and below it, cutting the boxes by a single plane severs two triangle regions that now lie on that three-dimensional plane. A three-dimensional lattice in three-dimensional space is generated by three basis vectors. Our first two basis vectors each determine a symmetric concentric box centered at the origin. Passing a two-dimensional plane through the corners of these boxes, we're able to determine two triangle regions. The location of this two-dimensional plane is determined by our third concentric basis vector, which travels from the origin to some point on this two-dimensional plane. The exact coordinates of our third basis vector can't be determined by the method we used to select our first two basis vectors. What we do know about our third basis vector is the three basis vectors together must maintain a fundamental region equal to 1. It means the volume determined by these three vectors must be 1. That gives us a range of possible locations, although not an exact point, for where the third basis vector can impact on this two-dimensional plane, which cuts the corners of the boxes. Our first two basis vectors must themselves determine a two-dimensional plane, because two basis vectors will lie on a two-dimensional plane. Our third basis vector does in fact translate this entire plane determined by our first two basis vectors up to some point on the first coset. And that is the plane that cuts the two corners of the box. To create a two-dimensional lattice, you need to know one lattice point, the location, coordinate location of one lattice point on the lattice, and you need to have two basis vectors. For the two-dimensional lattice, you need two basis vectors. So having the first lattice point, to get to the second lattice point, it's going to be the directed vector in this direction, and that takes you to the second lattice point. To get to the next lattice point, a second vector away, and the next lattice point, and more lattice points. Now we've got a one-dimensional lattice. So all these lattice points are one vector away, and the vector basis vector is in a particular direction and of a particular length or magnitude. When we use the second basis vector, which is in another different direction and of a particular magnitude, we can translate down our one-dimensional matrix, lattice, and translate it again up by the amount of the second basis vector. And we get another translate of our matrix. By this method, we can translate the one-dimensional matrix over and over again to populate the entire matrix, lattice. To get a third-dimensional lattice, you would need a third basis vector, and it will lift up this two-dimensional lattice to the third dimension. And on the third dimension, there'll be an exact copy of this same lattice using these same two basis vectors from the two-dimensional lattice. The exact location of each lattice point on the next coset, the next dimension up, the next higher up by one basis vector, the exact coordinates of all these lattice points is determined by where this third basis vector positions the one lattice point on the next layer. Because as we mentioned before, you can create the entire two-dimensional lattice with one lattice point and the two basis vectors. So our third lattice basis vector will give us the lattice point on the first coset, and we populate it with the two basis vectors.
Two vectors determine a two-dimensional plane. Integer multiples of the two vectors determine the lattice points upon that plane. Then these are the two generating basis vectors for this two-dimensional lattice. In order to create a two-dimensional lattice, you need two generating basis vectors and one initial lattice point somewhere on the plane from which you can populate the rest of the lattice. In this case, we have our generating basis vectors, so we know the relative position of all the lattice points, but since we are never given the initial lattice point, we do not know the exact position of the lattice points. Associated and corresponding to each of these two generating basis vectors is a triangle region lying upon the two-dimensional plane. The choice of the two basis vectors will determine the location of the triangle regions. For any choice of basis vectors, we have relationships that hold between the two triangle regions. Therefore, we do not know the exact position of the triangle regions. We do know information about their relationship to each other. We will prove that for any choice of basis vectors, with some restrictions, at least one of these triangle regions that correspond to that choice of basis vectors, at least one of those triangle regions must not contain a lattice point. And that's for any choice of basis vectors on a lattice with some restrictions. So, our proof, the two cases. Case number one, let's say that the yellow triangle region contains no lattice point. Then in case number one, we're done. One of the two triangle regions did contain no lattice point of the lattice. So case number two, some lattice point, and let us assume this lattice point, is contained in this yellow triangle region.
since we use the regularity of the distribution of all the lattice points, then we can say that if we translate this yellow triangle region by some integer multiple of basis vectors, then every lattice point on the plane will be contained within some translate by the initial basis vectors of our yellow triangle region. Now we're able to employ our second piece of our argument, the relationship between the red triangle region and this initial yellow triangle region. We're able to demonstrate by a system of parametric, simultaneous, linear equations, not linear, simultaneous equations and inequalities, that these two triangle regions must be independent of each other, disjoint, and they cannot contain a common point. Therefore, if the lattice point is assumed is inside the yellow triangle region, we know that this lattice point cannot be inside the red triangle region. The same argument can be employed for this translate of the triangle region and this translate of the triangle region. Furthermore, by an inductive argument, we're able to show that the red triangle region is to the right of this first triangle region. Therefore, it must also be to the right of the second triangle region, third translate of the triangle region, the next translate of the triangle region, because we're translating in the left direction. Therefore, by showing that our original yellow triangle region was already to the left of our red triangle region, we've demonstrated the entire row cannot be contained in the red triangle region. Employing that same argument on 10 different directions, we're able to establish that no lattice point could be contained inside this red triangle region. And therefore, for a broad class with few restrictions of generating basis vectors, we demonstrate that at least one of the two triangle regions does not contain a lattice point.
Minkowski's theorems help us locate lattice points. Consider an expanding Euclidean metric ball centered about the origin. Minkowski's successive minima theorem guarantees the first three lattice points, representing linearly independent vectors, will be a generating basis for the lattice. Minkowski's convex body theorem guarantees the maximum size for the ball before it encounters the first lattice point. Our method of choosing basis vectors reveals relative coordinate relationships between the lattice points. Parametric variables. When we assign parametric variables for the coordinates of our two generating basis vectors, v and w, we produce parametric equations for the vertices of the triangle regions. In this case, the triangle regions are disjoint when the W triangle region is entirely to the left of the V triangle region. This occurs when the first vertices of the W triangle region is less than the third vertices of the V triangle region in the x-coordinate. We see the inequality relationship that proves the regions must be disjoint. Translating by integer multiples of the basis vectors adds terms to the inequality. Proving this relationship proves the triangle regions are disjoint. From my thesis, Lemma 5.9, this relationship proves that triangles are disjoint for all integer basis vector translations in region 1. Given so we break this up and we use our first given, so greater than 1, we substitute. We put these two like terms together, and we can use our second given. So less than 0 and less than 0. And finally, employing our third given, we have the result. So for all of region 1, our two triangles will be disjoint. And by like means for every other region. We've proved the triangles must be disjoint for every point on the first coset. So in conclusion, let's look again at theorem 1.61, the existence of a dual pivot for every pivot. We prove that either V or W, the dual basis vectors, must be dual pivots, one or the other. The dual boxes contain no lattice points of the L coset. We know that because we expanded a systole cube in order to encounter the first lattice point on the L coset. And therefore, there cannot be lattice points inside the cubes on the L coset. On the first coset, we have proven by simultaneous inequalities that there could be no lattice points in one or the other of the two pivot boxes, V or W. So finally, by using mu r star less than 1 condition, we've limited my results so that the second coset cannot lie inside the pivot boxes. So we avoid the computations of lattice points on the second coset. Then, by definition of a dual pivot, one of either V or W must be a dual pivot, as their dual pivot boxes, one or the other, must be empty of non-zero lattice points. Thank you and appreciation to the San Francisco State University students who have worked on geometric representations of Littlewood conjecture with Dr. Yitwood Chum.